Black holes are invisible. That's kind of their whole deal. They don't glow, they don't sparkle, they just sit there eating. So when one of the closest black holes to Earth suddenly got bright enough to nearly see with your bare eyes, that was not ideal. V616 Monocerotis. On August 3rd, 1975, a satellite called Ariel 5 picked up an X-ray burst so intense it became the brightest X-ray object in the entire sky. Its optical counterpart, a star called V616 Monocerotis, brightened to magnitude 6.8, which is right at the edge of what human eyes can detect on a clear night. The cause? A black hole, actively ripping material off a companion star it orbits. Every 7.75 hours. That's a tight leap. Here's the unsettling part. We're not even sure how close it is. Some estimates say roughly 3,000 light years. Others, using newer data, say closer to 4,700. Scientists genuinely disagree. We also can't agree on how massive it is. Estimates range from about 3.2 solar masses to 11 solar masses, depending on who you ask and how they measured it. So we've got a hungry black hole somewhere in our cosmic backyard, and we're not sure how big it is or exactly where it lives. Lovely. But what actually happens when something gets too close? Gravity isn't uniform. The side of you closer to the black hole gets pulled harder than the side farther away. That difference in pull stretches you lengthwise and compresses you sideways. You become a noodle. That's called spaghettification. It sounds funny. It is not funny. Near a stellar mass black hole like this one, the tidal forces ramp up so fast you'd be shredded well before crossing the event horizon. So that's entry number 1, a black hole close enough to almost photobomb the night sky, and we can't even agree its stats. It only gets worse from here. Cygnus X1. In 1964, a suborbital rocket picked up a screaming X-ray signal from the constellation Cygnus. Scientists called it Cygnus X1 and then spent the next few decades arguing about what it actually was. Spoiler, it's a black hole. But getting the scientific community to accept that took an impressively long time. Here's the setup. Cygnus X1 is locked in a death dance with a blue supergiant star called HDE 226868, a monster with more than 40 times the mass of our sun. The two orbit each other every 5.6 days, and the whole time, the black hole is ripping material off its companion, just shredding it. That stolen gas doesn't fall straight in. It spirals, forming a superheated disk of material swirling around the black hole. This disk reaches temperatures in the millions of degrees and blasts out X-rays so intense we can detect them from roughly 7,000 light years away. That's called an accretion disk, and it's basically the black hole's dinner plate glowing white hot. Now, how massive is Cygnus X1? It depends on who you ask. Optical modeling puts it around 14 solar masses. But a 2021 study using radio astrometry from the VLBA revised it upward to more than 20 solar masses, making it one of the most massive stellar origin black holes ever measured electromagnetic. The distance estimates don't agree either, roughly 6,070 light years by one method, about 7,200 by another. Scientists are still arguing about this. Some things never change. But Cygnus X1 is just one black hole doing one thing, eating a nearby star. What happens when a black hole sits at the center of an entire galaxy? Sagittarius, a star. So far, we've been talking about stellar mass black holes, a few times the mass of our sun, snacking on companion stars. Scary, sure, but now we need to scale up. Way up. At the center of the Milky Way, about 26,000 light years from where you're sitting, there's a black hole with a mass of roughly 4 million suns. It's called Sagittarius A star, and every star in our galaxy, including ours, orbits around it. How do we know it's there? Because we watched. For decades, astronomers tracked stars circling an invisible point at the galactic center. One star, called S2, swung within 120 astronomical units of the black hole and hit 2.55% the speed of light. A star, moving at 2.55% the speed of light around something you can't see. That's how you weigh an invisible monster. Then, in 2017, the Event Horizon Telescope, basically a planet-sized array of radio dishes, observed Sagittarius A star directly. We photographed a shadow. Now, what makes that shadow? The event horizon. This is the boundary where the escape velocity equals the speed of light. Inside it, space-time curves so severely that every possible path bends back inward. It's not a surface, it's a point of no return. Cross it and nothing gets you back out. Not thrust, not light, not strongly worded emails. Right now, Sagittarius. A star is relatively quiet. It's not actively devouring stars or blasting jets across the cosmos. Dormant, not dead. On human timescales, no threat. On cosmic timescale, its gravity is the invisible hand shaping every stellar orbit in the Milky Way. So that's the supermassive black hole in our backyard. But at 4 million solar masses, Sagittarius A star is actually modest by supermassive standards. Some black holes make it look like a rounding error. Intermediate mass black holes. So we've got stellar mass black holes on one end, a few times the mass of our sun. And we've got supermassive black holes on the other end, millions to billions of solar masses. Logically, there should be something in between. Black holes in the range of about 100 to 100,000 solar masses, a middle child. A bridge between the small ones and the monsters. For a long time, scientists weren't sure that these things existed at all. They're called intermediate mass black holes, and they're kind of the missing link in black hole evolution. If supermassive black holes grew from smaller ones, there should be mid-sized ones hanging around as evidence of that process. But finding them is brutal because they're too small to dominate a galaxy's center and too big to form from a single dying star in any obvious way. The best candidate we've got is HLX-1, sitting in a galaxy called ESO 243-49. Mass estimates put it around 50,000 solar masses based on radio and X-ray scaling relations. It shows signs of an active accretion disk and has produced outbursts consistent with a seriously massive compact object. Another candidate, M82X1, clocks in at roughly 400 solar masses based on quasi-periodic oscillations in its X-ray emission, basically a rhythmic flicker that implies a specific orbital geometry around something very large and very dense. But here's the uncomfortable part. Most of these identifications are model dependent. We don't have direct stellar orbit measurements like we do for Sagittarius A star. Confirmed in this category means something much softer. It means indirect scaling, timing analyses, and a lot of educated squinting. Skeptics argue some of these signals could have alternative explanations. So intermediate mass black holes are the category where theory says these should exist. Observations say we think we found some, and the scientific community says maybe, but show me better proof. They're either the key to understanding how supermassive black holes form, or a gap in our knowledge we've been filling with wishful thinking. Speaking of supermassive, let's talk about the ones we actually can prove. Rogue black holes. Every black hole we've talked about so far is something giving it away. An accretion disk, a companion star, X-ray bursts, something. Rogue black holes have none of that. No orbiting matter, no glowing disk, no radiation of any kind. They're stellar mass black holes that got ejected from their systems, and now they just drift through the galaxy, completely invisible. And there are a lot of them. Population models based on stellar evolution estimate the Milky Way contains around 100 million isolated stellar mass black holes just floating out there, in the dark, doing nothing detectable. The only way to find one is if it happens to pass directly between us and a distant star, bending the star's light through gravitational microlensing. That's it. That's the entire detection method. You wait for a cosmic coincidence. And it worked exactly once with certainty. Between 2011 and 2017, MOA and OGLE microlensing surveys flagged an event, and Hubble followed up with years of astrometric tracking. The result? An isolated black hole roughly 7 solar masses sitting about 5,000 light-years away, cruising through space at around 162,200 meters per hour. A second candidate was found about 5,200 light-years toward the galactic center, also around 7 solar masses, but moving much slower, about 45 kilometers per second, which suggests it wasn't violently kicked from a supernova. It may have just quietly slipped away from its binary. So out of 100 million, we've confirmed one, maybe two. A rogue black hole gives zero warning, no X-ray glow, no radio emission, just silent gravitational distortion. The odds of one wandering close enough to mess with Earth's orbit are vanishingly small. But the uncomfortable part isn't the odds. It's that you literally cannot look for them. You just have to hope none of them are headed this way. So those are the loners. But what happens when two black holes find each other? Binary. Black hole systems. So we've talked about black holes drifting alone through the galaxy. Now imagine two of them falling toward each other, spiraling closer and closer, faster and faster, until they collide and merge into one. When that happens, the collision doesn't make a sound. It doesn't produce light. Instead, it does something weirder. It shakes the fabric of space-time itself, sending ripples outward at the speed of light. Those ripples are called gravitational waves. They stretch and compress everything they pass through, including you, including Earth, including the arms of a very expensive detector in Louisiana. On September 14, 2015, that detector, called LIGO, picked up a signal. Two black holes, each about 36 solar masses, had spiraled together and merged roughly 1.3 billion light-years away. The collision converted about 3 solar masses of matter entirely into gravitational wave energy. Not light, not heat, pure space-time vibration. And it did this in a fraction of a second. That event was called GW150914, and it was the first direct detection of gravitational waves in history. But here's what's really going to cook your brain. The amount that LIGO's detector arms physically stretched when that wave reached Earth, smaller than the width of a proton. They measured that, and it got crazier. In July 2017, LIGO caught GW170729, a merger that converted roughly 5 solar masses into gravitational radiation. In less than 1 second, that single event released more energy than our sun will produce across its entire 10 billion year lifespan. Just gone. Radiated as ripples in space-time, LIGO's first observing run produced 3 confirmed binary black holes. The second run added 7 more, including GW170814, the first event detected simultaneously by 3 detectors, LIGO's 2 plus Virgo in Italy, which let scientists measure the polarization of gravitational waves for the first time. Detection catalogs keep growing with each new observing run, and every batch raises fresh questions about how black holes this massive form in the first place, and whether some of them might have origins we haven't even considered yet. So we've seen black holes alone, and we've seen them in pairs. But what happens when a black hole sits at the center of an entire galaxy and starts feeding? Blazars. Up until now, every black hole on this list has been dangerous in a local, almost polite way. Get too close, bad things happen. Blazars are where we stop being polite. A blazar is what you get when a supermassive black hole at the center of a galaxy is actively devouring matter and firing out a jet of particles at close to the speed of light. And that jet happens to be pointed almost directly at us. We're staring straight down the barrel of a cosmic particle accelerator powered by something millions or billions of times the mass of our sun. The jet material moves at significant fractions of light speed, and because of relativistic beaming, the apparent brightness gets boosted enormously. Some blazars outshine their entire host galaxy by factors of thousands. They're among the most luminous, persistent objects in the observable universe, and they're unstable. The most extreme blazars can vary in brightness on timescales of minutes, not years, not days, minutes. That tells physicists the emitting region is absurdly compact because nothing can change faster than light can cross it. But here's the part that should actually concern you. Blazars are the leading candidate sources of ultra-high energy cosmic rays, particles that slam into Earth's atmosphere carrying more energy in a single proton than a professionally pitched baseball. That's not a typo. 1 subatomic particle, baseball energy. No accelerator humans have ever built comes close. If a galaxy within a few hundred million light-years developed an active blazar aimed at the Milky Way, the gamma-ray and high-energy particle flux could sterilize entire star systems, not just planets, system. So what happens when you point a telescope at the biggest, most famous jet in the sky? M87 star. For most of human history, black holes were math. Equations on a chalkboard. Predictions that made sense on paper but had never been seen. Then, in April 2019, the Event Horizon Telescope collaboration released a single image, and everything changed. A glowing orange ring with a dark shadow at its center. The first direct photograph of a black hole. And it was this one. M87 star sits at the heart of Messier 87, a giant elliptical galaxy about 53 million light-years away in the Virgo cluster. Its mass is approximately 6.5 billion solar masses. That's over 1,600 times heavier than Sagittarius A star. Its event horizon is so enormous that our entire solar system, sun, planets, Kuiper belt, all of it, would fit inside with room to spare. That result comes from the EHT Collaboration's 2019 paper in the Astrophysical Journal, Letters, Volume 875, in case you want some bedtime reading. But M87 star isn't just sitting there quietly being massive. It powers one of the most spectacular jets in the known universe, a beam of relativistic plasma blasting outward for roughly 5,000 light-years. Parts of it appear to move faster than light, which sounds illegal, but it's actually a projection effect caused by the jet pointing almost directly at us at near light speed. Totally legal, just unsettling. Now here's where things get philosophical. Even something this colossal isn't permanent. There's a theoretical process where black holes slowly lose mass by emitting tiny amounts of thermal radiation from just outside the event horizon. That's called Hawking radiation. For a black hole the size of M87 star, the temperature of that radiation is so close to absolute zero, it's practically nothing. The time it would take to fully evaporate is so long that the current age of the universe looks like a coffee break by comparison. So yes, even the monster in the photograph will eventually disappear. Just not anytime soon. Speaking of things that make our scale feel irrelevant, let's talk about something even bigger. TON 618. So M87 star was big, really big. 6.5 billion solar masses, jet shooting across thousands of light years, first black hole we ever photographed. Impressive stuff. TON 618 makes it look like a rounding error. TON 618 is a hyperluminous quasar sitting about 10.4 billion light years away in the constellation Canes Veneti. And when we say 10.4 billion light years, that means the light we're seeing left this thing when the universe was less than 4 billion years old. We're not observing TON 618 as it is now. We're watching a baby universe produce something absolutely unhinged. The black hole at its center has an estimated mass of around 66 billion solar masses. That's roughly 10 times heavier than M87 star, about 16,500 times the mass of Sagittarius A star. 66 billion suns crushed into a single gravitational point. At some stage, the numbers just stop meaning anything, and you're left staring at this, going, okay, sure. And it's not just sitting there quietly. TON 618 is in its quasar phase, which means the black hole is actively feeding at extraordinary rates. The accretion disk is blasting radiation across the entire electromagnetic spectrum, radio, infrared, visible, ultraviolet, X-ray, all of it simultaneously. At peak luminosity, TON 618 outshines the entire Milky Way by a factor of roughly 140 trillion. Not 140 trillion stars, 140 trillion times the output of our whole galaxy. It's less of a black hole and more of an engine that happens to have a galaxy attached to it. You'd think this is as big as it gets. You'd think 66 billion solar masses is where the universe draws the line and says, okay, that's enough. Yeah, it's not. Phoenix A. So we've seen black holes with masses in the millions, even billions of solar masses. But there's one that makes everything else on this list look modest. The black hole at the center of the Phoenix cluster's brightest galaxy, known as Phoenix A, holds the current record for the most massive black hole ever measured. Its estimated mass is around 100 billion solar masses. That's not a typo. 100 billion suns packed into a single black hole. Now, the uncertainty on that number is substantial. We're not talking about a clean, tight measurement, but even the lower estimates put Phoenix A in a category that barely has a name. Some researchers call these ultramassive black holes because supermassive just doesn't cut it anymore. The Phoenix cluster itself is one of the most extreme environments ever cataloged. It's one of the most massive galaxy clusters we know of, with hot gas cooling at an extraordinary rate and fueling star formation at levels that make most galaxies look lazy. And sitting right at the center of all that chaos is this thing. Here's what's wild. At this scale, the event horizon of Phoenix A would be larger than our entire solar system. You could cross it and not even notice. Seriously. The tidal forces at the event horizon of an ultramassive black hole are actually gentler than those near a small stellar mass black hole. The gravitational gradient is spread across such an enormous distance that you wouldn't get ripped apart at the boundary. You just quietly pass the point of no return. Kind of polite for something that massive. But the real question Phoenix A raises isn't about what it does, it's about how it got here. How does a 100 billion solar mass object form within the age of the universe? We don't have a clean answer. Current models of black hole growth, mergers, accretion, they struggle to build something this big in only 13.8 billion years. Phoenix A sits right at the edge of what our physics can comfortably explain. And that edge? That's exactly where things get weird. Because some black holes might not have formed from stars at all. Primordial black holes. So we've been talking about black holes that formed from dying stars colliding objects, or the slow accumulation of mass over billions of years. But what if some black holes were just already here? Like, from the very beginning. In the first fraction of a second after the Big Bang, the universe was an insanely dense soup of energy and matter, random density fluctuations, tiny patches where stuff was packed just a little tighter than the surrounding area could have collapsed directly into black holes. No star required, no supernova, just gravity and bad luck. These are called primordial black holes, and their predicted mass range is wild. Anywhere from something smaller than a grain of sand all the way up to thousands of solar masses. The smallest ones would have already evaporated through Hawking radiation. Remember that? The universe's slowest recycling program. Those tiny primordial black holes would have popped out of existence billions of years ago. But here's where it gets quietly terrifying. Primordial black holes are one of the leading candidates for dark matter. If enough of them exist in the right mass range, they could account for the missing gravitational mass of the entire universe without needing any exotic new particles. Just black holes. Everywhere. Invisible. Now, microlensing surveys and cosmic microwave background observations have ruled them out as all of dark matter across many mass ranges. But a window remains open where they could still be hiding in sufficient numbers. No primordial black hole has ever been confirmed. They remain theoretical. But the physics checks out. And the idea that dark matter might not be some mysterious particle, but instead billions of tiny black holes left over from the first heartbeat of the universe. That's the kind of thing that makes you stare at the ceiling at 3 a.m. Speaking of things that keep cosmologists awake, let's zoom all the way out. The Great Attractor. So we've covered black holes that eat stars, black holes that eat galaxies, black holes that existed before we even did. But there's one more thing on the list, and it's not a black hole at all. It's something bigger. Right now, the Milky Way, our entire local group of galaxies, and hundreds of thousands of other galaxies are all being pulled toward a single region of space at roughly 600 kilometers per second. That region is centered near something called the Norma cluster, about 150 to 250 million light years away. And for decades, we couldn't even see it, because it sits directly behind the plane of our own galaxy, in a zone so cluttered with stars and dust that optical telescopes are basically blind there. Astronomers call it the zone of avoidance. We knew the Great Attractor existed only because everything around it was moving wrong, galaxies drifting in directions they shouldn't be, at speeds that didn't add up, unless something massive was pulling them. In 2014, a team led by Brent Tully mapped the full structure responsible. They called it Laniakea, a supercluster spanning roughly 520 million light-years and containing over 100,000 galaxies. At the bottom of Laniakea's gravitational basin sits the Great Attractor region, and within it, the cores of thousands of galaxies, each with its own supermassive or ultramassive black hole, all contributing to a combined gravitational pull that has been reshaping the large-scale structure of the universe since before the Earth existed. This isn't dangerous the way the other entries were dangerous. There's no explosion, no spaghettification, no gamma-ray burst. The Milky Way won't reach this region for billions of years, but it is falling right now. And so is everything else nearby. This video started with a stellar mass black hole 3,000 light years away that briefly flickered into naked eye visibility. It ends here, with a gravitational sink so vast that entire superclusters of galaxies with all their billions of black holes are falling into it as you watch this sentence. Black holes don't just kill stars. At scale, they organize the universe. If you enjoyed this video and want to see more, click the video on the screen now